Let's start with something simple. A mass is connected to a spring on a smooth, frictionless surface. Because the surface has no friction, the mass can slide left or right without any resistance. Right now, the spring is relaxed. The mass stays still at what we call the equilibrium position. We mark this position as x equals 0. It's a natural resting point where no forces act on the mass. Now imagine we gently pull the mass to the right. By stretching the spring, we move the mass away from the equilibrium position.
When we let go, the spring pulls the mass back toward equilibrium. But because of its momentum, the mass overshoots and moves to the other side. The spring now compresses and pushes the mass back again. This back and forth motion continues again and again. We call it oscillation. Specifically, this is simple harmonic motion where the restoring force is proportional to displacement. The farther we pull the mass from equilibrium, the stronger the spring's force trying to bring it back. Now let's understand Hooke's law. The restoring force in a spring is directly proportional to displacement and acts in the opposite direction. F equals negative kx, where F is force in newtons, k is the spring constant in newtons per meter, and x is displacement in meters. When we stretch the spring, this creates displacement x from equilibrium. The spring tries to pull the mass back. This is the restoring force. Hooke's law tells us the more we stretch, the stronger the restoring force becomes. The negative sign means the force always opposes the displacement. Newton's second law connects force to motion. The net force on an object equals its mass times acceleration. F equals ma, where force is in newtons, mass in kilograms, and acceleration in meters per second squared. For our spring system, the restoring force causes acceleration back toward equilibrium. When we combine Hooke's law and Newton's second law, we get ma equals negative kx. This shows acceleration and position are directly linked in harmonic motion.
Let's understand the differential equation that governs simple harmonic motion. We'll start from the fundamental physical principles that describe how objects move under oscillating forces. Newton's second law tells us force causes acceleration. Hooke's law says the spring pulls back when stretched or compressed. M is the object's mass. K is the spring stiffness. X is how far the object is displaced from its resting position. Rearranging gives acceleration directly in terms of position. Acceleration is always opposite to displacement. The ratio k over n shows how quickly the system reacts. A heavier object means slower acceleration. A stiffer spring means faster acceleration. Acceleration is the second derivative of position with respect to time. The second derivative measures how quickly the velocity itself changes. The first derivative gives velocity. The second derivative gives acceleration. In simple words, how quickly speed is speeding up or slowing down. Position, velocity, acceleration, a chain of changes. Position is where the object is. Velocity is how fast, and in what direction, it's moving. Acceleration is how quickly the velocity itself changes. Now, we combine both ideas. Second derivative equals negative k over m times position. The further you are from equilibrium, the stronger the pullback. This formula exactly captures how oscillations happen. Here is the clean, standard form of the equation. Second derivative plus a constant times position equals 0. Acceleration and position always balance each other. This is the signature equation of simple harmonic motion. This equation predicts sinusoidal motion. The system oscillates naturally, with frequency square root of k over m. It describes everything from pendulums, to springs, to molecules.
Simple harmonic motion is a type of periodic motion. An object oscillates about an equilibrium position. The restoring force is proportional to displacement, as in F equals minus kx. The displacement varies sinusoidally with time. The equation x of t equals a cosine of omega t plus phi described SHM mathematically. Amplitude A is the maximum distance from equilibrium. It determines how far the object oscillates from the center. Higher amplitude means more energy and wider oscillation. Angular frequency, omega, tells how quickly oscillations happen. Omega equals 2 means approximately 1 cycle in pi seconds. Higher omega means cycles are closer together and motion is faster. Period, capital T, is the time for one full cycle of oscillation. T equals 2 pi over omega. Here omega equals 2, so T equals pi seconds. This means the wave repeats every pi seconds. Phase shift phi moves the wave horizontally. Phi equals pi over 4 shifts the wave by 1/8 of a cycle to the right. The white curve is unshifted. The pink curve is shifted. In summary, simple harmonic motion stems from the restoring force F equals minus kx. This leads to the differential equation x double prime plus omega squared x equals 0. The solution is sinusoidal with constants and phi. These constants are determined by the starting position and velocity. The final solution is x of t equals a cosine of omega t plus phi.